Hello everyone. Today we are going to see a new chapter in astronomy, Kepler's laws and the moon. And this is Dr.P.JAMUNA DEVI from A.D.M.COLLEGE. So today what we are going to see. First of all, we are going to discuss about Kepler's laws and the way how Earth obeys Kepler's laws. Some definitions on perihelion, aphelion, perigee and apogee. The moon obeys Kepler's laws, and again a few definitions like elongations, conjunction, opposition of moon and phases of moon. So first of all, let's start with the three laws of Kepler's. So Kepler's laws of planetary motion. So what Kepler has stated in law 1, he has stated that every planet describes an elliptic orbit around the sun being situated at a focus. Law 2 states that the motion everywhere in the orbit of a plane is such that the radius vector joining the sun and the plane describes equal areas in equal intervals of time. That is, the aerial velocity of a planet is constant. Law 3 states that the square of periodic times of planets are proportional to the cubes of their mean distance, the semi-major axis of their orbits from the sun. That is, T square is proportional to A cube. If capital T is the periodic time of planet, it is proportional to cube of the distance, that is A cube. Let us assume that distance equal to T. So let us recall some history behind Kepler's laws. Kepler published his first two laws about planetary motion in 1609, having found them by analyzing and astronomical observation of psychography. Kepler's third law was published in 1619. Kepler had believed in the Copernican model of the solar system, which called for circular orbits, but he could not reconcile Rahi's highly precise observations with a circular fit to Mars orbit. Mars coincidentally having the highest eccentricity of all planets except Mercury. His first law reflected this discovery. In 1621, Kepler noted that his third law applies to the four brightest moons of Jupiter. Gottfried Wendelin also made this observation in 1643. The second law in the area law form was contested by Nicholas in the book form 1664, but by 1670 his philosophical transactions were in his favor. As the century proceeded, it became more widely accepted. The reception in Germany changed noticeably between 1688, the year in which Newton's principle was published and was taken to the basic Copernican, and 1690, by which time work of Gottfried on Kepler had been published. So these are the interesting facts behind Kepler's laws. The Earth obeys Kepler's laws. So let's see how it happens. The Earth, being a planet, obeys the above laws. Therefore, the actual orbit of the Sun, Earth around the Sun, is an ellipse with the Sun at a focus. And the diagram you can see, the Sun is in the center. Earth is rotating in its orbit. So E0, E1, E2, E3, E4, E5 are the different position of Earth. Therefore, the actual orbit of the Earth around the Sun is an ellipse with the Sun at a focus. So in the same way, it can be proved that the apparent orbit of the Sun around the Earth is an equal ellipse with Earth at a focus. Now, we can assume that Earth is at center and the Sun rotates in the orbit. So S1, S2, S3, S4, etc. are the position of different position of Sun. Now Earth is at the center, and we can prove that the apparent orbit of the Sun around the Earth is an equal ellipse with Earth at its focus. So let us prove that the Earth is at a focus of this relative orbit of the Sun. The Earth, being a planet, obeys the above laws. Therefore, the actual orbit of the Earth around the Sun is an ellipse with the Sun at a focus. It can be proved that the apparent orbit of the Sun around the Earth is an equal ellipse with the Earth at a focus. In the first figure, let E1, E2, E3, etc. be the different position of the Earth in its actual orbit around the Sun years. Now, S1, S2, S3 are the apparent position of the Sun, assuming the Earth is at rest. Clearly, locus obtained by joining these positions is an ellipse equal to that of the actual orbit of the Earth around the Sun. It is proved that the Earth is at a focus of this relative orbit of the Sun. Now, let us see what is aphelion and perihelion. Aphelion is the point of Earth's orbit that is farthest away from the Sun. Perihelion is the point of the Earth's orbit that is nearest to the Sun. So in the diagram, you can see E0 is the nearest position to the Sun and E dash is the farthest position to the sun. So E dash is called aphelion and E naught is called perihelion. Again, some interesting facts. The Earth is closest to the sun at perihelion, 147 million kilometers. Every year on January 3rd, perihelion appears, and perihelion is the closest point in the planet's orbit to the sun. Let us see what is perigee and apogee. The moon's orbit around Earth is elliptical. The point on the moon's orbit closest to Earth is called the perigee. The point farthest on the moon's orbit away is the apogee. The diagram you can see the sun is at the middle and it is the moon's orbit. We can see the nearest position is called perigee and the farthest point of the moon's orbit is called apogee. The line of apsides. So what is the line of apsides? Apse in astronomy either of the 2 points on an elliptical orbit that are nearest to and farthest from the focus or center of attraction. The line of apsides connecting the 2 points is the major axis of the orbit. The point nearest the focus is the pericenter or periaxis. So we have a lot of definitions on apocenter, apoaxis, perihelion, aphelion, perigee, apogee, and periastron, apastron, and according to Jupiter we have 2 terms, perigeo and apogee. Let us see what is that. If the sun is the center, the specific terms perihelion and aphelion are generally used. If the Earth is at center, the terms perigee and apogee are used. Periastron and apastron refers to an orbit around the star. So when a star is involved, we have a term called periastron and apastron. Perigeo and apogee refers to an orbit around Jupiter. So now let's move to the chapter, the moon. Some interesting facts about moon. The moon is at a distance of about 240,000 miles from the Earth. It is the nearest celestial neighborhood to the Earth. The moon is a satellite to the Earth. It moves around the Earth following the law of Kepler. So already you have seen that that Earth also follows Kepler's law. Similarly, moon also follows Kepler's law. The moon is not a self-luminous body. It gets its light. It shines in the light. It receives from the sun. So everyone know the moon shines because the light from the sun. Sidereal month and synodic month. The sidereal month is the period of one complete revolution of the moon around the Earth relative to any fixed star. It is about 27 1/3 days. Let us see the definition of synodic month. The period of one complete revolution of the moon around the Earth relative to the sun is called synodic month. It is also called as lunar month or lunation. It is about 29 1/2 days. Let us find the relation between sidereal and synodic month. Let S, L, Y is the number of days in a sidereal month, lunation and a year respectively. That is S represent number of days in sidereal month, L represent number of days in lunation and Y represents number of days in a year respectively. In S days, the moon describes 360° around the Earth with respect to any fixed star X. Therefore, in one day, the moon describes 360 divided by S with respect to the star capital X. Similarly, in one day, the sun describes 360 divided by Y with respect to the star X and the moon describes 360 by L with respect to the sun. They get 360 divided by S equal to 360 divided by Y plus 360 by L. On simplification, we get 1 by S equal to 1 by Y plus 1 by L. So this is the relation between sidereal and synodic month. The diagram you can see, E is the position of the Earth, M is the position of moon, S is the position of sun and X is the position of new star. So we got the relation of sidereal and synodic month as 1 by S equal to 1 by Y plus 1 by L. Some interesting definitions on moon. Elongation of moon. The elongation of moon at any instant is the difference between the longitudes of the sun and the moon. It is said to be east or west according as the moon is on the eastern or western side of the sun. Relation between elongation of moon, longitude of moon and the longitude of sun. Let E be the Earth and S be the position of sun on the ecliptic. Let M be the position of moon in its orbit. And M1 is a foot of the perpendicular form into the ecliptic. So m1 is the foot of the perpendicular. So we can prove that elongation of moon equal to longitude of moon minus longitude of sun. So in the diagram we can see this gamma, that is the position of Aries, and m1 is the position of moon, that is projected from m. M1 is the projected line from capital M moon. Elongation of moon equal to first point of Aries m1 minus first point of Aries capital S. Capital S is sun, equal to SM1. SM1 is again equal to angle SEM1. By a property, we can say that SM1 equal to angle SEM1. If the inclination of the lunar orbit be neglected and the moon were taken in the ecliptic, then the elongation of moon is the angle subtended by sun and moon at the earth. So we have to write the relation between elongation of moon and the longitude of moon and sun. Next definition, let's see what is conjunction of moon. Moon is said to be in conjunction with the sun if it is seen from the earth in the same direction as the sun. At conjunction, the elongation of moon is 0 since it is in the same direction. Conjunction takes place on new moon days only. Opposition. Moon is said to be in opposition with the sun when it is seen from the earth in the direction opposite to that of the sun. This is just opposite to the definition of conjunction. So according to opposition, moon is said to be in opposition with the sun when it is seen from the earth in the direction opposite to that of the sun. At opposition, the elongation of the moon is 180 degree. Opposition takes place on full moon days. So how to calculate age of moon? The age of moon on any day is the number of days that has elapsed since the previous new moon day. It is measured only at midnight. The age of moon multiplied by 12.2 degree gives its distance east of sun, that is the eastern elongation of moon. Let us discuss the different phases of moon. The phases of moon are the different forms in which the moon is seen by a terrestrial observer. The phase of moon is mathematically defined as the ratio of visible portion of moon's disk to the whole illuminated disk. Let S be the sun, let E be the position of earth, and M be the center of moon. Moon receives the light from the sun in the direction SM, and its hemisphere ACB turned towards the sun is illuminated. That is, ACB gets light. The moon is observed from the earth in the direction EM, so that the visible portion is the projection of the illuminated portion on the plane LN perpendicular to the line of side EM. In the diagram, you can see the different position S, E, M, SM. The line ACB gets lighter, everything. So here X, D, Y, L is the lunar portion. Let D be the foot of the perpendicular from A on this plane, so that the visible portion in the area X, L, Y, dx, that is equal to, we can split it as semicircle XLY minus semi-ellipse XDY. So we can use area formula, area of semicircle and area of semi-ellipse. So we get pi A square by 2 minus pi AB divided by 2, where A is the radius of moon and B equal to MB. Let theta be the elongation of moon. Clearly we get angle ADM equal to theta. From the triangle AMD, MD equal to AM cos theta by triangle rule, that is B equal to A cos theta. Now visible portion pi A square by 2 minus pi A square cos theta by 2, whole illuminated disk equal to pi A square. Now phase of the moon equal to visible portion divided by whole illuminated portion. Now visible portion is 1 minus cos theta and whole illuminated portion is 2. So we get 1 minus cos theta divided by 2. Now to discuss the different phases of moon using the formula. So phase, already we got it as 1 minus cos theta by 2, where theta is the elongation of the moon. But when theta equal to 0, phase equal to 1 minus cos 0 by 2 equal to 0. So in the formula, phase equal to 1 minus cos theta by 2. Now we start to give different values for theta. Theta equal to 0. So what happens when it is a 90 degree? What happens when when we give theta equal to 180 degree? So when we give theta equal to 0, we get phase also 0. So the moon is new. So we completely cannot see the moon. When theta is less than 90 degree, cos theta becomes greater than 0. Therefore, phase becomes 1 minus cos theta by 2 is less than 1 by 2. Therefore, we can view the moon as moon in crescent form. So the moon is crescent. When theta equal to 90 degree, phase equal to 1 minus cos theta by 2 equal to 1 by 2. So the moon is dichotomized. That is, we can exactly see the half. When theta is greater than 90, cos theta becomes less than 0. Therefore, phase equal to 1 minus cos theta by 2 is greater than 1 by 2. Therefore, we can see the gibbous form of moon. When theta equal to 180 degree, phase equal to 1 minus cos 180 by 2 equal to 1. So when phase equal to 1, we get the moon is full. So we can view the full moon. So now we are going to see what is harvest moon. So we can see some interesting facts that how moon is helpful to farmers. The harvest moon is one of the most familiar moon names and refers to the nearest full moon to the autumnal equinox. The light of the harvest moon enables the farmers to work late in the night time, helping them to bring in the crops from the fields. This usually happens in the month of September. When the moon moves along the ecliptic, the retardation in the time of rising is del t equal to sin theta by square root of cos square pi minus sin square del L divided by 50, where theta is the inclination of the ecliptic to the horizon and del L is the daily increase in the longitude of moon. Del t is minimum when del equal to 0, provided theta is also minimum. Del equal to 0 gives that the moon is at gamma, but the inclination theta of the ecliptic to the horizon is minimum when the moon is at gamma. Therefore, del t is minimum when the moon is at gamma. That is, when a full moon occurs when the sun is near the autumnal equinox, the retardation in the time of rising of moon for the next 3 or 4 days is very small, so that the moon rise is not much delayed after the sunset. It is a harvest season for places at the northern hemisphere. The moonlight available immediately after sunset helps the farmers for gathering their harvest. For this reason, the full moon occurring when the sun is near the autumnal equinox is called the harvest moon. Let us see the definition of metonic cycle and golden numbers. Metonic cycle is in chronology a period of 19 years in which there are 235 lunations or synodic months, after which the moon's phases recur on the same days of the solar year or year of the season. The cycle was discovered by Meton, an Athenian astronomer. The golden number is a key part in determining the date of Easter, as it determines which year in the Metonic cycle we are currently in. It can be determined by the formula golden number equal to x mod 19 plus 1. Metonic cycles and golden numbers. Here 235 lunations equal to 6,939.69 days. That 635 lunations is equal to 19 tropical years. That is, a period of 235 lunations corresponds to a period of 19 tropical years, the difference being only 2 hours. Therefore, the sun and the moon come to the same relative positions in every such period, such that the phases of moon reoccur in the same invariable order in every period of 19 years. This period is called Metonic cycle. If the dates of new moons and full moons of the period be known, the dates of new moons and full moons in the succeeding periods can be predicted. This is very useful for recording the dates of many religious festivals which are regulated by the phases of the moon. Some of these dates were inscribed by Meton on public monuments in some parts of ancient Greece. Even now, the number which marks the rank of any one of the years in a cycle is called the golden number of the year. The Metonic cycle, now in use, has its starting point in the year 1 BC. Hence, to determine the golden number of any year, add 1 to the number representing the year, dividing the sum by 90. The remainder is the golden number of the year. When 0 is the remainder, the golden number is 19. For example, the golden number of the year 1965 is 9 and the 1975 is 90. Now let us calculate the epoch. The epoch of the year is the age of the moon on 1st January of the year. 1st January, 1st BC was a new moon day. The golden number of the year was 1 and the epoch is 0. Now diminish the golden number by unity, multiply it by 11 and divide by 30. The remainder is taken as epoch of the year. For example, when you find the epoch of the year 1952, the golden number is 15. That is remainder of 15 minus 1 into 11 divided by 30 is 4. Therefore, epoch is 4. Once again, we can see in another nice session of astronomy. Thank you everyone for watching.